We've got Greg Skidmore and Ben Hardy both taking turns to hand over the information. So, as I said, feel free to ask questions anytime. Guys, it's over to you. Thanks very much.
Okay, thank you, Graham. I'm Greg Skidmore. I'm the Director of Propagation Software at Remcom. I'm going to be joined a little later in this talk by Ben Hardy, an electromagnetic engineer, one of our physicists who's been doing a lot of work in this area. So I'm going to go through some basic background in range Doppler and sensing. And I oversee our products. We do software modeling and simulation. We're fully focused on electromagnetic modeling and simulation. And the areas that I'm involved in are wireless communications and the radar sensing. So today we're going to talk about radar sensing simulation with a heavy focus on modeling of humans and human micro-Doppler and a lot of other complications that we start to see when we start looking at sensing in detail. So a real motivation for this is that human presence detection is becoming very important in just about everything, all the industries that we support. In wireless communications and 6G, we're looking at integrated sensing and communications, things like intruder detection, search and rescue, health monitoring. In the automotive industry, in-cabin driver or occupancy monitoring systems, things like child presence detection, seat occupancy, driver impairment. So to us, predictive simulation it's a key tool that we developed. It's very critical in the design and early prototyping stages to evaluate systems, to design systems and evaluate their performance. So simulating radar returns of people, given all of these new and emerging technologies, is very critical. And it's much more complicated in large part because of the micro-Doppler that we see from movement of limbs, breathing, heart rate, a lot of these other things that we have to pick up are just a little more complicated than the traditional sensing where we're just looking at bulk moving objects in a scenario. A lot of what we'll show today, I think there was a question that we received even before the talk talking about other things. Micro-Doppler from other things can also be handled in a very similar way. But our focus today is going to be on people and the challenges that we see there. So we're going to talk about methodologies that we've come up to combine modeling and simulation, physical modeling of the human, and the human CAD model, along with ray tracing techniques that we can use to combine with that to do this type of analysis. And then, a lot of this is the motivation of what's going on in the industry and why we're taking an interest in this. But again, Remcom is all about modeling and simulation, and it's our sole focus. So this is important to us because it's important to the customers that are using our tools. And so our motivation is to make sure we can help them solve their problems in these challenging new areas. So radar sensor simulation, the main tool that we bring into this is a collection of ray tracing based techniques. Ray tracing gives us a way to simulate what's going on in an environment. We can pick up multipath, as we see with these ray path displays, whether it's an outdoor environment or an indoor environment. The things that we're interacting with that environment are absolutely critical, trying to understand what a radar sensor is going to see. So the ultimate result from multipath, like we see here, is a complex impulse response, and everything that we'll talk about next sort of evolves step by step from that kind of information about what the channel looks like, how things are propagating in that environment, and then taking it from there into post-processing. A lot of the things that we're going to show today are techniques that involve, as I said before, physical modeling and then post-processing to do things like range Doppler analysis. But we always I want to make sure that customers and people that look at these techniques understand that a lot of what we're doing is showing that these things can be done with the understanding that people will probably develop maybe their own more sophisticated signal processing. So what we show are some of the basic techniques for things like range Doppler, and hopefully that gives you the sense that you can get the kind of information you need to apply these techniques. And if you're going to develop something more sophisticated, you can add that to the post-processing. So some of the applications include automotive radar, outdoor, indoor sensors, in cabin we'll talk about later. And our tools in general can do far zone RCS calculations, but everything we're going to talk about today is really going to be closer in looking at the environment. So just to give a sense of what this kind of multipath looks like when we're in indoor scene, our ray tracing is capturing interactions on the way to a scatterer like a person or any other object in the scene, and it's capturing all the multipath back. So that gave you a little bit of a look of what it looks like when multipath is going through walls, diffracting through doorways, bouncing off of walls. capturing both the multipath to that person and also the multipath coming back is very critical to understanding what a radar is going to see. So some of the things that we put into these techniques just in the tool themselves are what we call targeted ray casting, where we can direct our rays to make sure that we fully illuminate a target, whether it's a car or a person. We're sending out rays so that we capture the illumination over that entire person or that entire vehicle. And this is important because one of the techniques that we're using is called physical optics. It does a surface integration over our target, and to get an accurate estimate of the backscatter, both in terms of magnitude but also phase, we really need to illuminate all of that target. And that is even more true when we start looking at micro-Doppler from small parts. If you're looking at things that are coming off of arms and legs, you need to make sure you're illuminating those arms and legs. So that's a very important part of the technique. We also have some careful techniques that we've developed that expand on this for multipath as well. That's a little more complicated to make sure that if we bounce off the ground and hit something, that ground bounce is also fully illuminating. If we bounce off a wall, if we diffract through a doorway, those paths also need to fully illuminate the person or the vehicle or whatever else it is that we're interacting with in the scene. So we've captured all of that into our technique. We have a technique called shooting and bouncing rays that's very commonly used in the industry, but then we also apply what we call exact path correction, which is a term that we coined based on a technique called image theory that takes every path that we found and corrects it so that we get an accurate magnitude, phase, time of arrival at the targets. We don't make far field assumptions. That was where we started long ago. We were starting with things like far zone RCS, but we moved very quickly beyond that to spherical wave and diffracted wave. And basically we can capture the wave fronts and the phase shifts that we see from one side of a target to another. And that also is very important. So all of this comes together, combined with the multipath that we showed before, to give us an accurate estimate of what is scattering back. So just a little bit about this shooting and bouncing ray technique. The technique basically shoots rays through a scene and sees which rays come close to something that you're interested in. That second step, though, is very critical when we start talking about when we're looking at things like MIMO, when we're looking at things like Doppler, correcting that path so that we actually know what has arrived at a specific point. And if we're looking at a radar sensor, we may have an array from MIMO radar where we actually need to know how much that path has changed when we move it over just a half a wavelength. So this exact path correction that we do has really given us a lot of capability when we start looking at things like MIMO, Doppler, and everything else that we'll be talking about today. We also bring in antenna patterns. Everything starts with the system and the antenna and characterizing that well. So a lot of times, as soon as we're doing any real analysis of an actual system, going beyond something generic like a dipole or just a basic pattern, we'll very quickly move to either a simulated pattern from a full wave solver or a measured pattern. And so a gain pattern has some complicated main lobes and side lobes. This is an auto radar antenna here. That's an example of something that we will pull into our software and make sure that we're using that accurate pattern in our simulations. Material properties are also critical. We can transmit through, reflect off of things, and how much is going to transmit through or reflect is going to be very much affected by the thickness of the wall, the materials it's made of, the surface of the human, the skin tissue, tables, furniture, other things in a scene. If we have windows, we may go through the windows of a vehicle. So all of these things are captured into our representations of the different things in the environment. Anytime you see me show examples of simulations and you see different colors, that most likely means that we have different material properties, and the colors are showing us the seat versus the car exterior. Sometimes for looks, we'll do things like the bumper will have the same color as the car, even though maybe the bumper is a composite and the frame is metal. So it's, there will be some cases like that where there are even more materials than what you're seeing. But when you see different colors, it's also a good indication that you're looking at different material properties as well. We've also brought in diffuse scattering, and this is particularly important in outdoor environments like a road, where we may be backscattering off the road. You can see that in addition to our normal, what we would call specular interactions, we're doing our surface integration, we're getting what's scattering off the vehicle and all of its facets using everything we described before. We can also pick up a lot of clutter, though, from diffuse scattering caused by the roughness of the road or the roughness of this surface. And so we've brought that in, and particularly where sensing is concerned, we've made a lot of extensions to it. We started with diffuse scattering looking at communications, And one of the things that diffuse scattering models typically will not tell you in the literature is the phase. So we had to make some extensions and enhancements to make sure we could model a randomized phase, but then make sure as things are moving through the scene, including the radar, that the way that that phase shifts is not just completely random. It needs to shift in a meaningful way so that we can capture Doppler from it accordingly. So we've implemented all of that as well, and that's been very critical to keep to including those in our calculations. So the dynamic motion of people, there are several things that make this, let's see. Let me make sure.
Hey, Greg, while you're looking at that, or Ben, there's a question here. Does REMCON have a library of materials? How's behavior being established?
We do. That is a great question. So we have a few different libraries in our sensing, we have a built-in library for our sensing applications that includes a lot of construction materials, things like concrete. It's tabulated over a wide range of frequencies. The same is true for things like roads. We have some different models that we include for salt water, and a lot of times for humans we'll use salt water. We also do have some other materials that we'll bring in. So we usually use a combination of things that are built in our libraries that you can just drag and drop into the tools. And then we also often will go to literature when we're doing something new and interesting, and in time those will make it into our libraries as well.
Great. Hey, thanks very much.
Okay, you're welcome. Okay, so let's see, my okay, so sorry, I had a little bit of trouble with my laser pointer. So this is an example showing communications between two people in the multipath as they're moving around. This is something, typically this would be for a communication link that we might see this sort of motion. And one thing you'll notice is the people were very stiff and moving around. As we start looking at sensing in Micro-Doppler and all the applications today, if we want to capture that effect, then we need to capture that motion as well. And so you'll see that these techniques we'll be talking about today, we are actually bringing in not just the movement and position, but the swinging arms and legs, and even the movement of the chest, and superimposing heart rate as well, as Ben will be talking to later, to capture very specific effects that we're looking for. So these three images here, I think motion can get complicated in a scenario, but these images show a lot of what we'll be talking about today, where the micro-Doppler comes in and how we can capture that in modeling and simulation. So to start with, we'll start with, of those things, the breathing and the vital signs, we'll do that a little later. But starting with walking, Micro-Doppler from walking, we see several different things. First of all, if you look at somebody, if you look at a vehicle and you're doing a range Doppler, you might see a nice constant 15 meter per second motion of a car that's approaching you. What you'll see with a person, there are a lot of changes going on. First, we have swinging arms and legs, and those are going to be picking up Doppler that's spreading. You might be moving forward while your leg is swinging back. And so you may see a Doppler go negative while the body's moving and giving you a positive Doppler. And the other thing that happens as well is we don't float along. As we move, we sort of lurch forward and then slow and go forward. So even the torso has a wave-like motion that's happening, and its Doppler is speeding up and slowing down. And all this is before we even start thinking about things like breathing and heart rate. So our approach to modeling this and trying to capture this accurately is to put this into our CAD models and to make sure in our modeling and simulation that we're capturing this as we're doing our simulations. We've developed a system for incorporating this motion into the models and for syncing things up so that as we're doing our simulations, we can have frames and chirps for FMCW synchronized so that we can do a set of simulations and post-processing that can give us INQ samples that are capturing this motion as we go along. So taking that walking person that we showed a moment ago, if we want to see what happens with the micro-Doppler, so this is a person that is on average moving at a speed of about 1.4 meters per second. But this is what the micro-Doppler is going to pick up. We can see Doppler going all the way into the negatives and all the way up to as high as 5 meters per second, simply because of all the small motions that are happening with different parts of the body. So one thing we thought we'd take a moment to talk about just briefly is the first thing people will ask about when you start showing new and interesting things in modeling and simulation is, what have you done to give yourself confidence that any of this is accurate, any of it's valid? So just thought I'd show a few things with validation, and then I'll go on into some applications and examples. So we did some comparisons. One thing that we'll often do that's within our control as a modeling and simulation company is we have a full wave solver. That's a solver that directly solves Maxwell's equations. This one is based on the FDTD, finite difference time domain technique. It's called XFDTD. And so we can run some simulations. Those typically have to be set in fairly small volumes because the jobs can get very large as you scale a problem to a large size. So we'll do a little comparison in a small environment, looking at a full wave solver, looking at scattering, in this case, shadowing from a person, and then comparing to the ray tracing. And this shows some comparisons between a few different ray tracing engines that we have, and shows that we're getting good correlation both in the individual field values and the CDFs of those values. We also looked at shadowing. So in this, in partnership with NIST, NIST did a fantastic job taking some measurements and capturing shadowing. In this case, it was between transmitter and receiver. And so we did a joint paper with them, taking their measurements and doing simulations, looking at uniform theory of diffraction ray tracing techniques and physical optics, two different techniques that we'd be happy to go into more depth with anyone who's interested, but today we'll stay at a high level. Usually with sensing, we'll use the physical optics. And part of the reason for that is we can get this very high level of detail in our models to do the kinds of things we'll be showing with the Micro-Doppler. But we were able to get from a simple model and uniform theory of diffraction a pretty good comparison of shadowing as a person moves through the beam. And again, with physical optics, very accurate representation as well. So this gives us some confidence that we can get some good shadowing modeling as we are passing between. And then looking at breathing and Micro-Doppler, we worked with NIST on this as well. They took some measurements, a very high resolution set of measurements, looking at angles of arrival and departure, looking at detail over time of breathing and heart rate. And Ben Hardy is going to be talking a little bit later about a little more of the details of how we went about doing the modeling and simulation. But just in terms of validation, you can see we get good comparison within a few dB between the simulations in blue and the measurements in red. And we get good correlation as well when we're looking at the phase and how the phase varies. And this again is, he'll talk about this later, but this is including both the breathing, the large spikes that we see, and you'll see some small fluctuations, and those are from changes that are happening due to heart rate. So through this process, we developed a way of modeling those two things, incorporating that into a CAD model like the one we show here, and then doing our backscatter off that CAD model and being able to pick up those effects. Ben's going to go into a little more detail on that later. So starting with some range Doppler and some impulse response, I thought I'd start with a fairly simple example looking just at the complex impulse response of what comes back from a scene. This is a Wi-Fi sensing example. We have done some work. There was a question that came ahead of time on this talking about Wi-Fi sensing. And I just wanted to mention that in addition to FMCW that we're going to be mostly focused on, which uses chirps, we have looked at OFDM sensing as well. We're not going to show that in this talk, but a lot of the things that we're doing with FMCW, we've done some preliminary work applying them to some post-processing with OFDM sensing as well. So it can be applied. It just has to be set up and structured a little bit differently, different way of getting to the frequencies and the times. But with some effort, that kind of post-processing could be done as well. But starting with just the impulse response, and then we'll build our way up from there. An impulse response can give us basically information about range. And it won't give us Doppler and it won't give us angles. So we'll step our way up as we go into the processing. So in this example, we have a person moving. We haven't yet incorporated the Micro-Doppler here. We did a simulation around 6 gigahertz, and we looked at several different bandwidths, and I've just kept it to 2, just so we can move through this quickly. So just comparing the lowest 20 megahertz bandwidth and the highest in our study, 160 megahertz, what we can see in this room is at 20 megahertz, the range resolution on a range estimation and then that'll feed into the range part of a range Doppler and everything else that comes next, is about 7.5 meters. So it's a very coarse resolution. And if we just, without doing any corrections, trying to subtract out anything and just looking at what we see, our impulse response is varying as the person moves into the room. But you can't visually, without probably further processing, really see anything here. Now, when we get to 160 megahertz, that reduces down to a little under a meter resolution. And if we look at our impulse response there, we can actually see the person moving through the room as this spike in the impulse response that's sliding a little bit closer in range with time. So this is using some broadband impulse response analysis that we have in some of our post-processing. Now, next we look at FMCW. In this case, we have an indoor millimeter wave radar sensor for people counting and tracking as somebody's entering the same room. Now, in this one, we took this up in complexity a little bit, and we now put in our walking person. We have a process where we can move a person, and it's essentially creating a sequence of CAD models and cycling through those CAD models in time, and then synchronizing that up with our chirp simulations so that we can see the scattering as the person is in motion. In this case, we went at 60, we're up at the 60 gigahertz band. We have some information about power. We're going to get to angle estimation next, and we have a field of view for that about 120 degrees, and we'll explain how we got there. And we've moved through about 11 positions here. So our range Doppler post-processing has several steps. The first is INQ generation. So we have some post-processing that takes an optimized set of simulations related to a radar frame. That frame contains potentially a large number of chirps, 128, 256, 512. And the specifications for that in terms of the chirp lengths, the spacing of chirps, and the numbers of chirps, the length, total length of your frame, will then determine things like the range resolution, the min and max range extents that you can resolve, the extents of the Doppler, and the Doppler resolution. So the steps in this include range estimation, which is done by doing a FFT on the INQ from a single chirp. The next step is to take that to velocity estimation. That will take a sequence of chirps and do a 2D FFT that has the range FFT and then another FFT across the different chirps to give you Doppler. And with that, you can create a range Doppler map like we show here. And then a third level that we'll show later is an FFT across the phasors from those range Doppler maps from multiple receivers. And when we get to that stage, we'll talk about virtual receivers. It can actually be a combination of transmitters and receivers that give you angular bins, so you can do angle estimation as well. So starting with the waveform, the chirp is basically a waveform that's going to go from a lower frequency to a higher. There may be a reset time. There'll be a sequence of these chirps. And from the lower to higher, you have a bandwidth, you have a sampling window. So there are several more steps here that determine the ultimate specifications. It starts with this, though. And we manage a lot of this with post-processing of our returns from a simulation. This is an example just of some of the specifications for this one. We have about a 2.5 gigahertz bandwidth on this, the sawtooth chirp that we talked about. You can see some things about chirp durations, 256 chirps per frame, some of the sampling information. So all of this is fed into our process, both to create the chirps for the simulations and then to post-process them afterwards to generate range Doppler. So the first step is the range estimation, and that basically is going to combine the returns with a reference version of the chirp signal through a mixer. And what that's essentially doing is capturing the delays by generating beat frequencies between the transmitted reference chirp and the received chirps. Those can then be FFT'd. The results of the FFT can be converted from frequency to a range, and you can generate a power spectral density versus range type of plot like we show here. Now, what we see in this are several spikes. From looking at these results and looking at a baseline before the person is introduced, we were able to tell that this is based on range as well. This is an interaction with the side wall. There's an interaction here with the far wall. There actually are some interactions that can happen with these walls as well, and there's an interaction in the corner. And there are also ghost images that appear when the person enters the room. At this point, the person is well into the room, and these images probably include reflections from the table, reflection from the back wall hitting the person in the back. And as we proceed through time, what you would see is this person is getting closer, and a ghost image might start getting farther away because it's the mirror image of that person. So you can see some things simply from this first step of doing range estimation. Now, the next thing we do is velocity estimation. We transmit several chirps. We do a 2D FFT across those chirps, and based on phase shifts, we can then determine the Doppler velocity. And you can see the person here, as we said before, they're moving about an average of 1.4 meters per second, but you can see we're picking up some Micro-Doppler here from the swinging arms and legs. We're definitely picking up some Micro-Doppler here in a ghost image. Oops. That's probably hitting the person in the back, bouncing off the wall. And there's some other things here that we just know are images of that person as well, caused by multipath, simply because we did do a simulation without the person, and we had these major contributions from the walls in the room. So as we go to this and look at the motion, you can see here's what the range Doppler is looking like with time. And as we think about what we saw before when we just had the walking person in free space, you can see a lot of that Micro-Doppler kicking in as the Doppler is spreading back and forth as the person is moving. And that, again, is because we're picking up swinging arms and legs and capturing that effect in our Micro-Doppler and in our range Doppler plots. Now, the last thing we'll do before I hand this over to Ben is angle estimation. So with angle estimation, if we have a transmitter and a number of receivers, we can do some angle estimation by evaluating the changes in path length, which are equivalent to changes in phase, from the received signal for those receivers. Typically, those receivers will be spaced somewhere on the order of a half a wavelength apart. In this case, we had a sensor designed to be looking somewhat forward, and we went ahead and moved those a little bit farther apart than a half a wavelength, and that narrows our field of view, as you'll see in the plots I'll show in a moment, to a little bit less than 180 degrees. And with the results that we get, we can then perform a third FFT. This will be across the range Doppler results, looking at phasors of the peaks across the ranges, and that allows us to then generate a range angle map. There are other ways that this can be processed, but this was one approach that we picked up to just be able to show this angle estimation technique. In the example I'm going to show, we actually have a MIMO system that has 3 transmitters and 4 receivers, and we space those carefully in a way that allows it to act as if we had 12 receivers, and that gives us 12 angle bins. And so this is what our array looks like. We have the 3 transmitters, we have 4 receivers. They're about half a wavelength apart. Transmitters are a little more than 2 wavelengths apart. And that allows us to then do this angle estimation that we'll show in a moment. And this is just a close-up, shrinking down those patterns so that we can actually see there actually are multiple elements in this antenna. And they're up in that corner of the room that we showed earlier. So if we just take our angle estimation for this case, this shows us what we're seeing in the motion here is the person. As the person's entering the room, they're moving right to left across that angular space, the field of view of the sensor. We have the back corner, almost directly across from our sensor. We have a wall on the left, a wall on the right, possibly some interactions happening with the alcove. The next thing we did is we took that the baseline without the person and we subtracted it out. And when we do that case, we can now get an even cleaner estimate of the angle. And this is focused mainly just on the person entering the room. We've now subtracted out the baseline of everything else, and now we can get a clear idea of where something in motion is in the room. Okay, so next, I would like to hand this off to Ben Hardy, a physicist at REMCOM that we introduced earlier. He's going to talk about Micro-Doppler due to breathing and heart rate and a few other applications.
Greg, hey, thanks very much. Just before we do that, could I just bring you back to a couple of questions that we've had on the, let me have a look. This first one was from Shooting, who Do you have simulation for 60 gigahertz OFDM Wi-Fi besides the Micro-Doppler? May be more important in Wi-Fi sensing. I don't know if you can talk to that at all.
We have not done simulations for Wi-Fi with OFDM sensing at 60 gigahertz, but we certainly could. I would expect there to be similarities. The differences, of course, will be different bandwidths, obviously slightly different specifications, and then the way we process it would obviously be different. But from the physical simulation of the person walking and of the electromagnetic waves, it's basically the same at that level. And then deciding how you're going to space them and how you're going to post-process them across subcarriers and the min and max frequencies and the timing of packets and things like that, that will obviously be very different at that stage. But the steps to get the data and the impulse responses would be very similar to what we were showing for FMCW at 60 gigahertz. And thank you for that question. Yeah,
thank you very much, Greg. Appreciate that. And I think Ben has answered the other questions there, so you might want to just look through that when he's speaking. Ben, okay. It's over to you, my friend.
All right, thanks, Graham. Thanks, Greg. Yeah, some really cool questions in the chat. We will definitely continue to try to answer those really interesting ones. I'll try to speak to some of them in the slides I do have. So we are looking at accurately simulating these human movements and then doing this dance between the validation of our simulation models with these accurate movements. And so there is sort of a back and forth there that we're doing to make sure that our movements and our simulation methods are sound. But this part of the talk, we'll kind of talk a little bit about that, and then how we use that model to generate specific data for the in-cabin example, machine learning, and then if we have time, SAR imaging. But yes, you can go to the next slide, Greg. So the first, Greg briefly mentioned this, the NIST measurements that we were really grateful to collaborate with them for. This is their TX and RX and LiDAR camera setup, so multimodal setup, measuring vital signs of a person sitting and standing in front of a sensor, along with the vital sign monitoring. Next slide. The measured data from this was the multipath components that were extracted with the SAGE algorithm, and we have the angle of arrival and azimuth and elevation and path loss and phase. So these really in the measurements, and that's just an example path from the chest from sampling. You can go to the next slide. Now, what we do for after we have this measured data, we want to simulate this breathing human. So what we did was we pulled an anatomical breathing model from the literature and estimated the heart rate as a sinusoid and overlapped those two. So the purple line here, R total, is the displacement from the breathing and the heart together. And so you can see you have this displacement of the chest, shoulders with just breathing, and a little part of the stomach moving with that breathing and heart rate. Next slide. And what we do is and there's some questions about this in the chat, we're controlling the CAD model by overlaying this waveform inside a blender. So we have explicit control of the heart rate, the breath rate, chest expansion, and the breathing waveform. And so Blender's state-of-the-art animation open source studio. And we've also, there's one question about this, taken LiDAR data from the multimodal NIST measurements and also have a process where we translate that into Blender. You can go to the next slide. So once we have this breathing model, we can simulate it in our tools, right? So this is the full wave simulation, which we already showed. And obviously this would take a really long time. But one thing I wanted to point out is we can start making assumptions about our human model. You can actually see that there's not very much penetration of the fields for this 28 gigahertz plane wave into the human. So really it's almost, the electric field's almost zero here. So we can begin to make assumptions about our model using our full wave techniques. Such as determining the importance of different materials inside of the cabin and how far the waves penetrate through the foam, or maybe if they reach the metal frame within the chair. But full wave kind of allows us to ask these questions and answer them at these high frequencies and smaller scenarios. Next slide, please. So back to the breathing. From the measurements, we have this data, and we use this measurements to inform our simulated model. And one way that we did that is we were able to estimate the displacement due to the breathing for the specific subject using the power spectral density. And so we can estimate the movement from the breathing and then also the displacement due to the heart rate by simulating a similar scenario and seeing at the same frequencies and seeing where we get the same power. And so there's also some signal processing where we remove some of the low frequency bias in the EM data, which is also done in the measurement data, but you can go to the next slide. For the ray tracing simulation, in this case, this is run on a local machine, so the time is a little bit larger than it would be if it was run on a cluster or a highly parallelized simulation. This is one breath sampled every 50 milliseconds to make a 2.4 second breath. So 2.4 seconds divided by 50 would be the number of simulations. Then we're using skin material properties from the literature. And then our chest movement from breathing was about 3.5 millimeters from the measurements. And then the heart rate we estimate was from 0.4 to 0.8 millimeters potentially from the heart rate. And this is the same dimensions of the person, distance to the transmitter and receiver, and the height of the receiver. You can go to the next slide, Greg. And from this, you can see that we have, as kind of Greg already mentioned, a really nice correlation between the measurement and simulated phase without bias correction. And so you can see that the chest or the person is moving slightly or swaying as they're sitting on the table, which is expected across 25 seconds. You can go to the next slide. With bias is on the right side and without bias on the left, and so we can use our other camera, our other data to inform how the person is moving and to reproduce the results and get something very, very highly correlated. So you can go to the next slide. So this data is, part of it was published in the IEEE radar conference last year. And then we also have a full publication coming by Sfogato, who's done a lot of this work where he's integrating these multimodal sensors. And so he'd be the one to talk to about using others' data to bring that into the simulation. You can go to the next slide. So getting into the in-cabin sensing portion, now that we are confident in our breathing model, we can use it in in-cabin sensing. So next slide. For in-cabin radar, we already touched on this. It's becoming a standard feature in advanced driving assistance systems, and it provides detection methods while also maintaining privacy of the drivers or occupants. And it can be used for driver alertness, safety features, or detecting unattended children and pets. Next slide. So for this example, we're using a child CAD model and overlaying that same breathing waveform that we have confidence in on the model and placing the child in the cabin. So we can go to the next slide. And here we validated this with a simple plane where we overlay this breathing to ensure that we're getting range Doppler from a movement, from these small movements of the chest. I'm moving the simple plane with that breathing waveform, and you can see that we're picking up range Doppler right in the velocities that we expect as the plane moves towards the radar and then away. So towards in minus Doppler velocity and then away in the positive. Next slide. So then we place different radars in the cabin. So we're looking at 2 different radars here, one in the cabin light or roof mounted, and then the rear view radar, and then 2 placements of the child, one in the center in the back seat, and then also one in the behind the driver's side. Next slide. And you can see that just the child alone, we get a really pretty clear understanding of what's going on here. Notice that the velocity is in millimeters per second on the bottom. And then when we add the foam car seat, just one material foam, obviously you'd probably want something more complicated potentially, or not. I'm not actually sure. We haven't done that study yet for the kids car seat. There's not much difference there, but as soon as we add the car, we get something at the range that we expect, right? About 1.4 millimeters or meters away from the rear view radar, but we begin seeing all of this clutter begin to dominate the range Doppler from the breathing. And so clearly we need more, there's denoising methods or object localization would be really helpful here. So next slide. For the other radar placements, very similar story, especially for the roof-mounted radar. We see distances that make sense, you know, and remember that the chest and the stomach are, that whole plane is moving. So it makes sense that we're seeing movement with the rear view radar across a small range of, across the range of the child's chest, right? So, and then similar to, so we could start doing things like subtraction or maybe even machine learning on data sets like these to determine occupancy detection or likelihood of seating. So kind of moving into that direction, you can go to the next slide. We want to use this foundation to start looking at other scenarios, but also considering likelihood estimation, maybe even point cloud algorithms to determine where the occupants are in the vehicle. And then introducing more complicated scenes like opening of a door or a moving car or pets or non-human moving objects, as was mentioned in the chat, which is really important. But we haven't even really touched on. We've done some studies on the importance of the seat fabric and the materials, but every car is so different that, in a way, each car kind of deserves its own attention. We can move to the next slide. So because we've been doing all this, we have a really easy feature to use where we can have, if you have a Blender model, you can actually import it directly in our software. So here's an example where I'm importing our walking human right into our software straight from Blender, and we have all these specific CAD frames of the walk. This is a decimated version, so less animated frames than, just a few less, just to show the import process. So the next, kind of leading into in the last few minutes here, thinking about this data that we're creating, this simulated data, we can move into machine learning applications. So I have a small example of that that I want to show next. Next slide. So the idea is we want to generate this training, validation, and testing data from our validated simulated data, and then feed a convolutional neural network all of these, the phase from the radar, and then the breathing waveform, to predict the breathing waveform and classify it as either normal breathing, hyperventilation, hypoventilation, or even breathing that would be correlated with driver drowsiness potentially. But these are the 1, 2, 3, 4, 5 breathing types that we're classifying into. Next slide. So what we do is we capture synthetic data of the breathing humans, human models with different frequencies, amplitudes, and inspiration ratios, which this goes back to the anatomical model that we showed earlier. Next slide. And we begin to create this data set of breathing humans and train a model to predict the breathing waveform and classify it. So here I started with a normal distribution, but you can see that the model, the predictions in the red are actually struggling because the normal distribution is kind of centered around normal. But if we go to the next slide, if we look at a synthetic data that has a uniform across a wide range of different values, amplitudes, IE ratio, breathing frequency, the model does a lot better. And that's what's powerful about this is simulation, right? We can control these scenarios. We can control and do anything we want, really. We can make the person breathe really fast, which might be really hard to do in the lab, to get someone to breathe that fast hundreds of times, right? They would probably have some problems afterwards. So it's cool that we can control this in simulation and create these maybe even impossible measurements to train a model to predict these moments really well. We can go to the next slide. So these are the results, and I don't really have time to go through all of them, but this is only trained on 200 waveforms, which only simulating only took about a day, which is really not that long for for machine learning models, which often take a long time or a lot of data to predict. So I'm just trying to show that in about a day of simulation time, you can create a data set that is rich enough to predict something complicated like this. You can go to the next slide. So I don't have a lot of time to go through the SAR imaging. I just wanted to mention this briefly. So maybe just go to the final slide, Greg. So we have an application to run through this ultra wideband. So SAR imaging often uses a wide band of frequencies. And we have an application to essentially ray trace once on a single frequency and then get that wideband frequency response of the reflection off the human. And you can see that the image of the human here for a really large array, the difference is, and on the edges is only about 5 dB. But on the surface, it's a little bit lower. So we have methods to do SAR imaging as well. And I just wanted to mention that, although it's a little bit different from what we've mentioned before. But yeah, you can go to the next slide, Greg. Yeah, so that's everything. Thanks for hanging in there with me as we went through all those slides. But we'd love to answer any questions you have.
Hey, thank you, Ben. Appreciate it. Just one question that's just come up from Dr. Vitaly Najudin of Rogers. What's the minimum object size you can detect and use to analyze micro-Doppler signatures, e.g. such an identifying insects based on specific wing sweep behavior?
That is a very interesting question. A lot of it is, it just depends on our ray tracing settings. And I think this is I hadn't thought about insect sizes, but it's a perfect application for that targeted ray shooting that we talked about. We had to put that in mainly to deal with very sharp edges of things like corner reflectors, making sure you're hitting them. But the same is true if you're trying to hit something very small. The targeted ray shooting will allow us to hit something at a very small size. I think we'd probably have to look at ranges and other things to see if you ever start to get into GPU precision type stuff at a very distant range. But I'd be very interested in learning more about your example. But I do think there's a lot of flexibility on size because of those techniques that we have.
Excellent. And Vitaly, obviously, the guys we can follow up. You guys can follow up individually afterwards if you want to go deeply into any of these applications, etc. So Bo Anderson has just asked, is the micro-Doppler millimeter wave imaging all active, or are you applying it into a passive mode at all?
Another great question. So the simulations that we're doing we've been looking at active systems, but Really, with the simulation, we could do something that's passive as well. We would just need to set up the post-processing to determine how to capture the right data from simulation to be able to do the processing. So it would be, so we have these pre and post-processing techniques that are setting up this FMCW. We'd have to set up something a little bit custom for a different system. But once you've done that, it's the same kinds of simulations, I think, whether it's active or passive.
Yep. Great. Thank you. Marco, at millimeter waves, you normally have a channel sampling rate of 1 to 3,000 hertz. Do you produce as many CAD models? How much time for simulation and with a human walking?
We do not have to simulate every single sample point. That's a really critical thing in the simulation that we've done. So we've developed an optimized process with the ray tracing that captures what we really need to capture in the ray tracing is the motion. If things haven't moved very far, one of the critical things is we're actually capturing path by path. So in those scenarios we showed, we may have 20,000 or 40,000 individual paths, and we know how much each of those propagation paths has changed over maybe a series of a few milliseconds. With that, we can estimate what's happening between those. So we can then adjust all of those paths over frequency and time to get to these samples. So that's been a very critical part of the optimizations. So a frame of chirps then that lasts maybe a few milliseconds might just take 2 simulations and a lot of post-processing. As far as runtime goes, it really does depend. There's a lot more multipath in indoor enclosed environments than the outdoor environments. So a simulation that takes a couple of minutes in an outdoor might take a few tens of minutes in an indoor, and then you can decide how much multipath you want to pick up with ray tracing settings. So that one I don't think I can answer quickly on this, but we could certainly have a discussion afterwards and talk about those nuances and the environments and everything else.
Great, thank you. Okay, apologies if you already covered any of this stuff, but I'm just going to go through some of the questions that came in prior to the actual webinar. So Mike Shaw from Marata asked, does this include a driver monitoring system to observe if a driver is impaired or distracted, or is it simply just looking at using the radar?
The simulations that we do are all focused on basically on radar frequencies, on RF or EM modeling and simulation. A few hundred megahertz up to 100 gigahertz is kind of the range that we typically are operating in. So it wouldn't be including LiDAR or cameras, if that's really the question. Now, every now and then people will start using radar for some of these other systems as well, and in that case, we certainly could simulate that. Yeah.
Interesting. We got a couple of questions from telecom operators, obviously looking at this whole joint communication and sensing model that's quite hot at the moment. One here. And you did talk about it earlier. I'll just run through it for those people that didn't see this so that they know what you were referring to earlier with the Wi-Fi. So it says here, the webinar, what insights can be drawn from the human modeling approach directly towards Wi-Fi sensing? You kind of covered that earlier, I think. How does your human modeling methodology differentiate between human micro-Doppler signatures and those from other moving objects or environmental clutter, especially in dynamic indoor-outdoor scenarios? And in the context of in-cabin child presence, how does your model account for challenges posed by different car seat types, vehicle vibrations, and the presence of other objects and occupants in the cabin? A lot of stuff there, Greg, but I don't know if you could just speak to that maybe briefly.
Yeah, I think we did touch on some of that a little bit. I think the key is that what we are doing is modeling the physical changes. So if you're looking at rotating tires or other moving parts, as long as we can build up a model, basically a method for making the physical CAD model move, we can then predict what reflects off of it. So that's really the key, is we're really going down to the physics, modeling the interactions individually, and we're modeling the motion by moving the CAD models around. So if we move something else, we could do that as well. And as part of this, the indoor materials, Ben, did you want to jump on that one at all? Or I can. It's
busy answering the question, actually.
Oh, okay.
What was the question?
I can take it. It was about seat materials, and I think you touched on that a little bit for car seats and car.
Oh yes. Sorry, I don't remember the question.
That's okay. I can take it. So I think the The bottom line is we've had some interactions with customers where we've looked at different seats, and I think it's really just a matter of modeling the properties. There are some things with foam and seats that are a little more complicated, and we're going to be continuing to look at dealing with the thickness in the ray tracing in different and new and expanding ways. So there's a challenge there. And with car seats in particular, the metal structure inside, it's not just the surface CAD model, you also have to have the metal structure inside. So there's some differences there that we've been looking at so that we can go into a seat, diffract around the metal frame, and then exit the seat. So there's definitely some interesting, pretty much anything you look at with this, there's some interesting complications to tackle for sure. So thank you for that question.
Okay. All right. Well, listen, Greg, Ben, thank you very much. And also for a couple of your colleagues, Taryn and Ruth, for answering some of those questions in the chat as well while we've been going along. But we've just about run out of time. So it's been really interesting. As you can tell by the number of questions that have come in, you know, the attendees are certainly interested in the topic, and I'm sure there's an opportunity there for you to follow up with them individually afterwards and touch on any of those points that have been brought up during the webinar. So a big thank you to everybody for coming on board today and going through the webinar, and a huge thank you to Greg and Ben for taking us through the details from Rencom. So really appreciate it, guys. Really interesting stuff, and look forward to seeing you maybe in Singelfingen in Germany at the end of this month or some point in the future. Thanks a lot, guys. If you've got any questions, you know where we are.
Thank you, Graham. Thank you, Tom and
you.
Debbie, for organizing.
Yes,
Pleasure.
thank you. Thank you very much for the opportunity to let us have this talk. We really appreciate it. And thanks everyone for joining. Really appreciate that too.
Thanks a lot then. Bye-bye for now.